Okay, can you all hear me? Is the audio okay? Okay, so welcome back everybody, and I hope you had a great break and got back with recharged batteries. Now we are back in the last 7 weeks of the semester, and the topic today is in a way to wrap up a discussion of the harmonic oscillations and look at driven and damped oscillations and see what kind of interpretations we can make. And we're also going to link this topic up with the coming homework. And also in the homework next week, we're going to have one exercise about the classical pendulum, or the mathematical pendulum, as we've been calling it. And then on Wednesday, we are going to look at something which is a slightly alternative way of looking at harmonic oscillations, which many of you will encounter in essentially all physics courses. And that's about a Fourier analysis of harmonic oscillations. And that's an extremely useful tool when you want to interpret these type of physical processes. So harmonic oscillations, they play a central role in essentially all fields of physics. And it spans from you riding on a gravel road and suddenly you hit a washboard. You probably encountered that kind of situation. And then the way you can damp your bike or your car is essential to the way you hit the washboard, or the way you just tune your radio to the right frequency. So we are going to look at some of these technicalities and how we can interpret the calculations and the results of the calculations which we obtain. Homework number 6 is a kind of a strange mix of optional exercises, but also kind of repeat of what we have done. We're actually asking you to make a kind of summary of what you have done till now. This is something which can be useful in a way to just just restart the batteries again, right? This was what we did before spring break. If you're like me, I would have forgotten everything after spring break. So just getting restarted and look at what we have done. And then there is also an optional exercise which gives you an additional score about a kind of mini evaluations. So we are in the middle of the semester, and it's always good to get a feedback from you guys, whether we're on the right path, if there are things which we need to improve upon, if there are things which are unclear, if things are not working well, or if things are working well and you're happy, that's even better, right? But all kinds of feedback is extremely useful. So then we have at least some time to correct our path. And there are also some optional exercises. And one thing you're going to see in the coming homeworks, there will be exercises which give you an optional score in case you didn't have time to answer all the exercises in previous homeworks. Okay, so let me just dive into the small reminder of what we have done. So I'm going to mainly use the whiteboard. I'm going to switch between the whiteboard and Jupyter notebooks. Yes? So I'm planning to have them out by Wednesday or Thursday this week, if that's okay with everybody. So you should have them back in 2 to 3 days. Actually, I would like to comment upon that because the midterms were excellent. Thanks to everybody. You did a great job here. Goodie. So let's switch to the whiteboard and just go through some of the material which we're going to cover today and remind ourselves about some of the technicalities which we did before spring break. So the equation which we have been looking at is the equation for a harmonic oscillation with a linear term in the unknown quantity x. So what we've been having is the mass, this is the acceleration term, multiplied with the mass. So this is the force. And then we had a term which depends on the velocity. And what we assumed here is that the friction or the damping or the air drag or whatever is something which has a linear dependence upon the velocity. It does not need to be the case. So remember that friction or resistance or damping is something which we don't have a fundamental force for, unless we would like to run a calculation at the microscopic level. But when we do the kind of phenomenology here, this is something which we would then have to compare with the experiment, whether the air resistance or the damping or the friction term is something which is proportional with the velocity. So we also assume that there is a constant here. This constant may depend on external conditions like temperature, pressure, and so on. So it doesn't need to be a constant of temperature and pressure, but we're assuming it's a constant. And then we had a term which is linear in the unknown quantity x. And so this is what's normally called a second order linear differential equation, because we have a term which runs like x itself. When we go to the mathematical pendulum, we have something which depends on sine of the angle theta. And then we say that we have a nonlinear term. A nonlinear term gives rise to a much richer set of solutions, actually, and much more complicated physics. It leads, amongst other things, into what we normally call chaotic motion. And we are going to explore some of these things by running it numerically next week, when you're going to take the program from this week and simply replace that with a nonlinear term. And then you're going to study the classical pendulum. And then we could apply an external force, which we simply call f of t. And a very common one is to have some amplitude. And then we have a frequency omega. It could be a cosine, it could be a sine, or it could be a linear combination of cosine and sines. So this is a pretty common force which you could apply to a system. So one thing, coming back to you riding on a gravel road and you encounter a washboard, one of the things you will notice is that this washboard, they actually come at very regular intervals. And they look almost like a kind of sine wave, actually. So they're just small bumps which come at regular distances. That's actually a very interesting physics case. Why does the sand and gravel pile up in such regular distances? But for us, as driving a car or riding a bike, this sounds like a kind of regular set of bumps which just pop up suddenly. And whether your suspensions are good or not is something you will feel immediately. Okay, so the things which we did was also to introduce this natural frequency. And that was given in this particular case, is given by this specific material constant divided by the mass of the object. We defined a new parameter we call gamma, and later we are going to change that a little bit to something which you will encounter in the literature, something which is called the quality factor. But let's now just keep it as this. So you see now that this gamma is normally something we would call a material specific or system specific constant, because it depends on the variables which define our system. So our system is defined by the mass, it's defined by this resistance or friction term, B, and then it has this natural frequency, omega, 0. And these are all system-dependent parameters. As you can see here, everything here is defined by your specific case. So when you come to the physical pendulum or the mathematical pendulum, then this k is going to be replaced by the gravitational acceleration, and m is going to be replaced by the length of the pendulum. So just keep that in mind, that you have physics-specific constants or system-specific constants, and then you may have some fundamental laws which act on the system. Then the other thing we did was to introduce a dimensionless time. So I'm just reminding you a little bit of the things which we looked at. So omega 0 is a quantity which has dimension inverse time. It's a frequency. And then we could rewrite the equations in the following way, where we also had defined, so we actually divide by the mass and we divide by this omega 0. So we redefined everything like this, and then we had a new term omega tilde, which is omega divided by omega 0. Then we could rewrite the differential equation in terms simply of this dimensionless time plus this parameter 2 times gamma of dx dt. So the equation now has dimension length. Gamma is a dimensionless variable, as you can see by checking the dimensionalities. Tau is a dimensionless time. So we have introduced some dimensionless units here, which make it convenient when we are solving things either analytically or numerically. So the way we would solve this analytically is the same. We would do the same scaling, whether we do this analytically or numerically, just to get rid of all the constants. And then we had a plus an x, and then we had this f tilde 0, and then we had a cosine of omega tilde times tau. That was the equation we ended up with. And then we found that this equation could be written out in terms of what we called a particular solution, which depends on tau, plus a homogeneous solution, H, which also depends on tau. And in our case, what we had is that this is given by, since we had a cosine factor, we had a cosine of omega times tau minus a phase shift, which we could define. So this is what we have in here is the particular solution. So this is this one. And then we had the homogeneous solution, which is the case with damping only. So that means that the solution which you find in the next step here, so we had this was defined in terms of a minus an R1 times tau plus a C2 times an E over minus R2 times tau. And R1 and tau would depend on this variable gamma. So R1 was given by minus gamma plus gamma squared minus 1, and R2 was given by minus gamma minus gamma squared minus 1. And depending on the value of gamma, we could get an imaginary root, or we could have a real root. If we had a real root, that was ended in a case which we called critical damping or overcritical damping. If we had an imaginary root, that means that gamma squared was less than 1. Then we ended up in what we called underdamping. But all these solutions which we have, so let's just frame them in here again. So these solutions here are what we call the homogeneous solution. That means that we have no particular force which is being applied. So when we have this specific force here, what happens, and as we saw when we run the calculations, is that after a specific time, a time tau, then the solution is dominated. X is governed, not dominated, but it's actually governed by this particular solution, xp of tau. So if we take a look at what we might expect when we look at these solutions, if we now look at this applied external force, F of tau, and we put it as a function of tau here, this is a regular term, so it's a cosine in our case, so it looks like this. And we would have, this would repeat itself with a given period. So this is something which we call a period, T, and that's defined, as we saw in the beginning or before the spring break, by 2 pi divided by omega. That defines the period. So remember that omega is inverse time, given as a function of inverse time. It's a frequency. So 2 pi divided by omega defines the frequency and the period of this quantity here. This is our f of t. When we then plotted over x, what we saw then is that in the beginning, depending on the initial conditions, we could get something which looked like this, a little bit wiggly, and then suddenly the regularity of the cosine kicks in. So what we normally call, so this would be then governed by the same period of the applied force. Now, this means that when you look up in the literature, you will find names for the damped solution. So this is normally called this phase here. This contains info from XH, so the homogeneous solution. And they're normally called in the literature, they're called transients, transient solution. So that means that there is a transition from one type of motion to, in our case, a regular type of motion. And then what happens then is that what you get is a sinusoidal motion. So what kicks in here at this specific point is actually x of p. That's the one which governs from here and on. And this regularity you see in terms of the sinusoidal oscillations, these are normally called attractors. So the system gets attracted to a specific frequency, which then determines the motion of the system. So these are just names which you will find in the specific literature on harmonic oscillations, whether you're looking at a pendulum, whether you're looking at a harmonic oscillation like this one, or you're doing electronics. You will see the same names. You will see transient solutions, attractors. That's when the system gets attracted to a stable set of solutions, and that is the one which dominates for all time. So in the beginning, there will be some memory which links back to your initial conditions and the damping term, but then the force takes over. So what we are going to do now is just to look at examples. And we are going to look at a specific case now with some input values. So let's try to pick some specific values. And then we're going to run it numerically and see what happens. So let's now plug in omega, which is equal to 2 pi. So we simply assume that. And then I'm going to have a frequency, natural frequency, which is larger than the applied external frequency. So I say that omega 0 is 5 times omega. I'm simply going to put the mass equal to 1 for simplicity. I'm going to put this F0 to 1,000. And then I know that this F0 tilde is going to be 1,000 divided by the mass times omega 0 squared. So this becomes 1,000 divided by 100, because it's 2 pi, 2 times 5. So that's obviously 10. And then I have pi squared. So this is approximately 1.01. I'm just putting it to 1. I'm scaling the equations. So this choice of F0 is something which I just picked in order to scale the equation. So I get an F0 tilde, which is close to 1. There's nothing more mysterious than that. I've also defined the period here for my oscillations. So that means that when I take this term here, it means that the period it's going to oscillate with is going to be given with 2 pi divided by omega. This means also that I need to set up this omega tilde in my equations when I want to solve the equations. And that's omega divided by omega 0. And that's 1.1 divided by 5, 0.2. And then I need to plug in gamma, which is equal to the parameter b divided by 2n of omega 0. And I'm going to choose a value for this b. I'm going to choose this b, which is simply equal to omega 0 divided by 20. So that means that my gamma is going to be equal to 0.025. And then I'm going to make a selection. I'm going to put the system at rest. So I'm going to put them to 0. So these are just choices we are making here, right? So let's see now what happens. So one thing you should keep in mind, because we are going to see a small problem when we're going to make the plot here. So remember also that t is equal to tau divided by omega 0. So that means in our case, this is going to be tau divided by 2 pi times 5. I'm taking away the units here because it's going to be it should come out in seconds or time. So this is just 10 tau divided by 10 times pi. So we have to be a little bit careful when we now are going to plot the results. So this is just an example we can play around with. Note one more case here. So I've chosen this value of B to be pretty small. And this is normally what you may see in many physical realizations of these kind of systems. So if you take this parameter B, you see now that it is actually smaller than omega 0. So this is a kind of physics assumption we have made. We are just saying now that this friction term or this resistance term is a small term compared to the natural frequency of the system. So in many physical realizations, this is actually the case. So friction can often be a very small term. That's actually important for the damping of the system. So now we are making an assumption which is also reflected in many experimental realizations. If you take a classical pendulum in one of the standard grandfather clocks, you will often see that B is proportional to omega times 0.01. So there's a ratio of 100 between B and omega in a typical grandfather clock. If you then want to relate this to some specific physical situations or realizations of it. So this will always be something which depends on your system. And keep also in mind that when we set up the differential equations, we opted for a system where the resistance is proportional to the velocity. Times are constant. This is model dependent. And clearly you can run these calculations and then you can compare them with experimental data and see if this assumption is a realistic assumption or not. Okay, so let's take a look at the calculations now. So let's go back and look at the Jupyter notebook. And let me just bring that up. So let's take a look. This is essentially the same type of codes which you have seen now tons of times. And it's pretty close to the one which you did in homework in the midterm. So we are setting up this 0.0 delta t, that's the time step. And now I put up a final time, which is 20 here. And you're going to notice a small problem here. Then I put the initial conditions, initial position and velocities to 0. I put the mass to 1. I define omega to be 2 times pi, omega 0, as we wrote down on the whiteboard. So these are basically the input variables which we need to set up. So what I would expect now is something which now, after some initial wiggling and damping, the force which I've applied should kick in. So let's just run it and see what happens. This doesn't look like what I promised, right? Because what I promised you, so let's just stop sharing and go back to the whiteboard. So I promised you something which may look like this. So if we now look back here, so we should see something like this. But my calculations didn't look like that, did it? So let's go back to the Jupyter notebook. So this is what I would like to see. So there must be something wrong in my calculations here. So let's go back. So in the handwritten notes, I put up a relation between the dimensionless time and real time. The plot which I made on the whiteboard was in real time, not a scale time. So if you look at what I have here, what could the problem be? Yeah? Yeah. So I have to go back and multiply with the right factor, which in this specific case would be 10 times pi. Or what I could do now is just extend the time to the final time, which is larger, right? So if I do that, so let's see what happens. So let's go back then and simply put a 200 here and just rerun. And now you see, well, this is exactly what we expected. So you see in the beginning, you see now the so-called transient terms, which are doing something strange. So the system hasn't settled yet. But then when you reach now a specific time here, so which you have to scale with 10 times pi in order to get back to real time, because now this is my dimensionless time. So real time is a dimensionless time divided by this frequency omega 0. So what you would see then, if you look at the frequency and the period, you would then see now that you have these tops which repeat themselves in a very regular way. So you have the transients which dominate up to time in this dimensionless time to 100. And then after time, dimensionless time equal to 100, these information gets washed out. And then it's simply the applied external force which now dominates the rest of the behavior of the system. So these are the kind of things which you will see when you deal with systems which have oscillations. And now what we are going to do next now is try to look at things like how does this term, which has to do with a special or the particular solution, how does that behave as a function of the frequency? Are there some ideal frequency which will maximize the amplitude? Like when you are tuning in, or if you have done that, I guess many of you have not used a normal radio anymore. So this is something like 10, 15 years ago. You would just actually tune in the radio to the right frequency. So tuning in the radio to the right frequency is something which leads to resonance. So that means that the natural frequencies of the radio hit the frequency of a wave which are sending in, or the radio wave. So let's look more at the kind of mathematical analysis of the solutions which we have. So this is what you will expect when you have a so-called applied force. And these are normally called driven oscillations. And you see very clearly that the information about the initial conditions is simply lost when you're now into times from 200 and beyond. Any questions so far? Does this sound obvious or not obvious? But to me, it was not obvious. It took me some time to digest it. Okay, so what we're going to do now is to look into a topic which is very, very important when we're dealing with oscillations. And this is a concept which is called resonances, and how you can tune the system so that you can get the proper behavior. So as I mentioned, with me biking on a gravel road with a washboard, and normally I come with a road bike, and that has no suspension at all. And when I hit the washboard, can be pretty painful sometimes, especially if you have a high speed. So the way you would then tune the suspensions in a car is something which is very important. The other example is you tuning a radio frequency. So let's look at the mathematics here and the concept of resonances. Resonances is something which you will encounter again and again in physics, whether you're doing quantum physics, electromagnetism, you're doing optics, basically all fields of physics where some kind of oscillation kicks in. So let's take a look at that specific aspect. And let's go back to the whiteboard. So our next topic is now going to deal with what is normally called resonances. So when we look at this particular solution here, the x of p of tau, this was given by an amplitude d times a cosine multiplied with this dimensionless frequency minus this phase shifts delta. Now, what we did last week, now before spring break, was actually to derive this quantity, which now is given by this particular force which we're applying. And we found that this d is given mathematically by something which looks like this, squared plus 4 times omega squared times this parameter gamma squared. And these are the parameters which we defined a little bit earlier. Now we can rewrite this term. We can also square it if we want. So let's take and square it. So this is the amplitude. So that's an F0. And this is now divided by 1 minus omega squared. And one of the things I'm going to do now, for those of you who have looked into the textbook by Taylor, is I'm going to reintroduce some of the constants so that the equation you're going to see now matches what you will see in the textbook of Taylor, which, by the way, is an excellent textbook. So we have I'm going to redefine some quantities. Oops, what happened here? Okay. So I have so sometimes what happens is actually that my iPad just goes down, and I don't know why. It's happened before. So it just needs some few minutes to reboot, 1 or 2 minutes. In the meantime, we can just take questions or other things. I'm not gonna expose you to my horrible jokes. Actually, I only know one joke, according to, yeah. So let's say, I actually had some problems with my iPad lately. It's getting old now. So now it comes back, hopefully. So let's see now. Okay, so I'll go back again. So if it had taken longer, you might have been exposed to one of my horrible jokes, but it came up again. So let's go back to the equations here. So we have we are going to define F0, which is simply write as this. Let me just rewrite it here. So I write this F0 squared tilde. So I'm going to square this constant p. So this is F0 divided by m squared. And it's given by the frequency, the natural frequency to the power of 4. And I'm simply going to call this term here with the F0 divided by m squared. I'm gonna call this one F0 squared, like this. Then I'm going to multiply, if I now square this equation, I'm going to multiply out omega squared, omega 0 squared. So if I rewrite this one, I can actually write it like an F0 squared. So I'm just multiplying out omega 0 squared plus 4. And I have introduced a new term here, which is beta omega squared. And this beta is something which I have defined as b divided by 2 times the mass of the object. And remember that that term we had, gamma, was given by b divided by 2m omega 0 squared. So the thing you can do now, you can tune either omega 0 or you can tune omega. So the most natural, so you have different physics applications. So you can tune omega and keep omega 0 fixed. And find maximum D. Alternatively, you can now tune omega 0. So this is also possible. And keep omega fixed. Now, if you think of the harmonic oscillator, which you have, the system which we have been studying, if you were to run an experiment, which one of these quantities would be natural to tune? Would it be omega 0 or omega? Yeah?
Omega, because if you want to tune omega 1, then you have to actually physically change your sign.
Exactly. Excellent. So this is one of the things which you have to think of, but you can have physical situations where you can tune omega 0. but normally you're limited by, in this specific case, by the materials which you have at hand. So that means that it would be more natural to tune omega. Now, if you look at the equation for D here, if I now want to find out what kind of situation can maximize this amplitude of this the particular solution. So what is your feeling? How would you proceed if you want to find the frequency which maximizes the amplitude? Yeah?
Take a derivative and then find an equal zero.
Okay. So the way you would proceed, as Elia says, is to take the derivative of the equation and find what maximizes or minimizes. Do we need to take the derivative of the whole equation? Or is it sufficient to look at just one part of the equation for D? What is your feeling again? Do we need to minimize or maximize? Any good feeling for that? So if you look, so this is the equation which we want to maximize. So what happens if my denominator is at its smallest value? Then it maximizes D, right? So what I could do now is simply to say, instead of maximizing D, I minimize the denominator, right? So I can simply take the derivative of the denominator, and that's going to give me the frequency which maximizes the value of D. So we said that the typical situation which we encounter is a situation where we would end up in a situation like this, where we can tune omega and keep omega 0 fixed. So in order to find maximum D, we minimize the denominator. Minimize the denominator. So whether I take the maximum of D squared or the maximum of D, it doesn't matter. It's actually easier to take the derivative of the denominator squared. So what I'm going to do now is simply to find the quantity which maximizes or actually minimizes the denominator. Squared plus a 4 beta of omega squared equal to 0. And when we take the derivative, we get minus 4 of omega squared minus omega plus 8 times beta squared times omega equal to 0. And then we divide with omega on both sides, and we have assumed that omega is different from 0. Doesn't make any sense because we have to set omega equal to 0 because we have assumed now that we have a driving force, right? So having a driving force means that we must have a frequency which is different from 0. Else it doesn't make much sense to define a driving force. So when we do this, what we find then is that omega is given by omega squared, 0 squared, minus 2 times beta squared. So that's the value for omega. And if we now look at the value of beta, which we have assumed to be much smaller than omega 0, that means often that there is a little difference. There's not a much difference between omega and omega 0. So that's not an uncommon situation which we have for the maximum frequency. And you see now that the maximum of this equation here, so if we now have a situation where we put omega 0 equal to omega, what happens then is that this amplitude D is now simply equal to F0 divided by 2 times beta multiplied with omega 0. So this is the typical place where we have a maximum amplitude. And you can see that because when you go back to the equation here, you would have D when we now put omega 0 equal to omega. then we get this F0 tilde, F0 tilde divided by the square root of omega 0 squared minus omega squared. And since we put them equal, this is 0. And then we have plus 4 times beta squared times omega 0. So when we have that situation, we get an amplitude which is pretty close to the maximum value, because if you look at the argument which we put up here, assuming now that beta is much, much smaller than omega 0, which is not uncommon in an experimental realization. If we make this assumption that omega 0 is almost close to omega, then here, what we did here was simply to say that they are equal. And then we have a pretty simple equation here, which says that D is given by this term here. Now, this does not need to be the case, because you may have a beta which may not be much smaller than omega 0. But if that happens, then you will see a maximum, which is pretty close at the driving frequency being equal to the natural frequency of the system. Now, the kind of situation which you will often encounter then is something like this. So if we now look at the value of D, so we are now tuning everything in terms of frequency omega. And then we would get a situation where we would have a value of D, which looks something like this. So it peaks around omega 0. Now, one thing which is interesting, and you can see that from the expression which you have here, from this particular expression, is that if I now decrease my beta, what happens if I decrease beta? So if you look at the expression which you have here, and you go back to the graph, suppose this is now a result which has been achieved with beta equal to 0.1 times omega 0. Suppose now I increase the value of B with respect to omega. What does your intuition say about the behavior of this curve? Will the curve be sharper around omega 0? Will it be larger? Will it be a higher spike? Or will it have a smaller value? So what is your feeling here? What will the curve look like if I now put the beta equal to 0.3 times omega 0? Yeah? Yes. So when I increase now, if I have a larger friction term with respect to the natural frequency of the system, my peak is going to get broader and it's going to be smaller. So if I now decrease the value of this parameter beta, so let's change color here. So what I would get then, when it's out here, it would still be the same, but then it would look more like this. So this will be my beta equal 0.3 times omega 0. So as beta decreases, then the resonance peak gets higher and sharper. So let's write this down. So as beta decreases, which we define to be B divided by, so let me just quickly remind you of that. So we have beta, so these are natural constants of the system of 2m decreases. The resonance. So the fact that we have a resonance means that we get a sharp response to the applied frequency. The resonance gets sharper. So this peak, which you see, is normally called a resonance. So the peak gets sharper and higher. So if I have a radio where now I'm tuning in the frequency, which doesn't match perfectly well this kind of natural frequency, then what will happen then is that my signal will be a little bit blurred, right? But if I can really get a sharp signal, which is really focused around the specific frequency, then I should get a crystal clear voice popping out of the radio, or some music, if you prefer that. Okay, so the thing which we are going to do now for the remaining minutes is to look at some other definitions. So in the literature, you're going to encounter something which people call the quality factor. And that's just a way to rewrite what we have seen here in terms of a new constant, which many people actually plug into these differential equations. And let's just look at this quantity, because it's an interesting quantity, because you can relate that to the period which is given by the driving frequency. So this is the final thing which we're going to look at now. And then we have many of the basic ingredients which we can use when we now are going to analyze this type of harmonic oscillations. So in the homework which you have now, essentially what you will do is to look at just a damping case with no driven force. But there is an optional exercise where you can add a driving force. But then next week, when we're going to look at the mathematical pendulum, we are going to look at the effect of a driving force. And then this, many of these quantities which you have seen here are quantities which you will use in the physics analysis of a mathematical pendulum. So let's take a closer look at some further analysis of what we have done here. Now, so what we said now, we assume that omega is equal to omega 0. And that leads to a maximum frequency or maximum amplitude, which is given by this physical constant, F0, divided by 2 times this parameter. We have this parameter beta. Sorry, it's actually, see, beta times omega 0. So let me just rewrite it, because this is not F0 tilde, that's actually F0, the way we define things. So if we now use this value, we could now ask the following question. What is the value? We are going to define a specific value. The value of d max of d, which is equal to 1/2 times d max, which simply means that we have an F0 divided by 4 times beta of omega 0. This defines what we normally call a width. Defines a width. Or what's normally called a full width at 1/2 maximum. Which, so this width here defines, this width is defined, sorry, which is defined, which is given, or which is defined by the interval between, and this is probably the last thing we get to today, between the 2 points where d is equal to 1/2 its maximum value. This was not a very good phrase in English, actually. So one of the things you will see now, if we make a plot here, is if we take and square the value, we have a top around omega 0. And we can actually show that this width, where we get half the value, is given by this omega 0 plus this beta, and omega 0 minus beta. So it's going to look something like this. So this case here, actually this graph, this should actually be half the value, half d max. It doesn't look like half d max. But this width here is now given by a distance which is called 2 beta. This term is going to define something which we call the quality factor. So this defines. And on Wednesday, we're going to discuss a little bit more in detail how we can use this quality factor in the studies of harmonic oscillations. So this quality factor is given by a Q. I'm just setting up a definition now, by omega 0 divided by 2 beta. And our time is out now. I wanted to bring up this definition. And then on Wednesday, we are going to look at how we can use this definition to say something about the behavior of the system. And for those of you who are going to study this type of oscillations, you will encounter these definitions and these kind of interpretations. Okay, so we are going to hang around. If you have questions about exercises, other things, feel free to hang around. We're also doing the standard office hours on Tuesdays, Wednesdays, Thursdays, and then we have Julie's office hours, we have Georgia's office hour, we have Abby's office hours. Please feel free to use these. If not, we will see each other and pick it back again on Wednesday.